Welcome to the debate. Our subject today, it really dives into one of the most intellectually compelling challenges in comparative cognition, the complex xenoneurosemiotic adaptations of Lepidoglossum sapiens. This is a truly unique species whose entire sensory cognitive apparatus has, it's evolved to parse these incredibly high-density visual languages and multi-species cues. I mean, it's a creature that essentially reads the world as an evolving text.
And we're using the human aesthetic interface of Zoetica Ebb as our central case study, which is a fascinating lens. We're observing how this species processes her deeply complex, symbolically saturated self-fashioning. And the core text, it really details a form of cognition that is profoundly hybrid. It's both neural and microbial.
Exactly. Which brings us to the central, foundational question we're facing today. Is the remarkable cognitive capacity of Lepidoglossum sapiens primarily a function of its evolved neural architecture, so its specialized brain structures, or is it fundamentally dependent on the active, symbiotic modulation that's provided by bacterial and microbial coagents within those very circuits?
Right.
I'll be arguing for the primacy of the evolved neuromechanisms, and I think I can demonstrate some deep structural parallels to established, albeit highly specialized, mammalian cognition.
And I'll be coming at it from a different way. While the neural architecture is, of course, crucial, I'm going to argue that the active trans-kingdom symbiotic relationship is what fundamentally defines and executes these unique cognitive functions. And this, I think, forces us to redefine core concepts like self, attention, and memory. It positions the microbial co-agents not as support, but as essential active computational modules.
So my position is really rooted in evolutionary pressure and structural efficiency. Lepidoglossum sapiens lives in an ecology that is just saturated with shifting, sometimes deceptive visual symbols. So to survive, its neural system had to develop a specialized feature we call glossophagic invariance. In simple terms, this is the cognitive ability to identify semantic meaning, the prey of information, if you will, even when the physical symbols are dramatically transformed, warped, or partially obscured.
Now, I contend this isn't some radical new system, but a sophisticated exaptation of established learning models. Specifically, the hierarchical structure of the species' visual system shows, the text says, remarkable parallels to mammalian inferior temporal processing, which is the brain region we know is responsible for object recognition. This hierarchical, competitive neural architecture was naturally selected for its speed and its efficiency in these unstable biosemiotic ecologies. The microbial elements are certainly important scaffolds for optimization, sure, but the core mechanism of semantic recognition resides in the dedicated neural structure itself. It functions as the primary semiotic translation engine.
That's an insightful framework, and I particularly appreciate the emphasis on evolutionary necessity. However, I maintain that this system, it can't be reductively explained by referencing neural parallels alone. The sheer novelty of the data compels us to define Lepidoglossum as a hybrid biocomputational entity. You see, the microbial agents are not passive scaffolds. They're active tacticians. They're executing cognitive maneuvers that the neural substrate alone, it just can't perform efficiently or robustly.
Right. The key functions, especially those allowing rapid adaptation to novel semiotics, are demonstrably driven by this symbiotic interaction. For example, the cortical microbiome, specifically Xenobacillus glossophagy, it actively secretes neuromodulators. The source text shows these chemicals literally bias gradient descent and trace learning. So if we simplify that, the bacteria are externally coaching the neural network on how to adjust its learning rate and its weight assignments. This makes the bacterial influence a physiological parallel to temporal difference learning. So if critical processes like generalization from a limited training set are being actively modulated externally by a non-neural agent, the system is fundamentally a distributed trans-kingdom process. And the radical implication here is that the cognitive self is redefined as a semiotic interface that spans multiple biological kingdoms.
That brings us directly to the central tension, doesn't it? The locus of invariance. You argue the bacteria are driving the learning, but the translation invariance itself, that core capacity to maintain the stability of recognized meaning across semantic mutation,
it's a pathogenic necessity, right? It's necessary because the symbolic environment is almost viral. This is achieved by the brain's own architecture, recurrent collateral connections that functionally implement what's called a glossophagic attractor basin, constantly pulling sensory input towards semantic coherence.
Okay.
The visual system's deep similarity to mammalian IT structures suggests that the neural wiring provides a structural mechanism for robust, fast recognition. The capacity for invariance, much like face recognition in primates, is structurally inherent.
I appreciate that evolutionary framework, I really do, but the data on active microbial modulation seems to fundamentally undercut a purely neural explanation of stability. I'm just not convinced that the neural structure alone is sufficiently robust. The stability of that recognition is shown to be conditional.
How so?
Well, the source material explicitly notes the functional requirement of microbial agents for stability in all but the most idealized conditions. The text points to the recruitment of glossophage biofilms along the lateral geniculate pathways. These neurobacterial consortia, as they're called, are shown to be necessary to stabilize attractor states, and crucially, they actively compensate for cortical magnification loss at peripheral eccentricities. So, if the ability to recognize an object collapses outside of that foveal-like region without the microbial consortia present, if that stability relies on the bacterial layer to function beyond the central visual field, then the system is necessarily hybrid. It suggests a neural capacity is brittle and relies on the transkingdom consortia for operational stability in a real-world, messy semiotic ecology.
That's an interesting point about peripheral loss, though. I would frame the distinction differently. The fact that the attractor networks do maintain robust recognition when solitary objects are presented on blank substrates, even across eccentricities, that clearly mirrors mammalian findings where competitive clutter is minimal. This suggests the neural framework intrinsically allows the function. The structure is capable of the invariance. The bacteria are therefore functioning as a sophisticated compensatory mechanism. They're compensating specifically for the intense competitive suppression that occurs in complex semiotic-rich environments. They are a highly specialized adaptive layer for ecological management, but the neural architecture carries the initial fundamental capacity for invariance.
But that just raises the question, doesn't it? Why would an evolutionary necessity, survival in a hostile symbolic ecology, create a neural structure that is so brittle it requires external agents for compensation outside of laboratory conditions? Doesn't the sheer energy cost and reliance on external microbial populations make a purely neural solution evolutionarily preferable, given the massive selective pressure for quick autonomous parsing?
That's a probing and a vital question. I think the answer lies in the speed of the semiotic evolution in their environment. A purely synaptic internal solution would be slower to adapt to rapid changes in symbolic language. The symbiotic relationship provides a low-cost, high-speed evolutionary pathway. The bacteria are a fast-mutating, fast-responding regulatory layer that allows the neural system to maintain a structurally efficient but potentially brittle core architecture, while offloading rapid adaptation and clutter management to the symbionts. The hybrid model allows Lepidoglossum to keep pace with the pathogen-like speed of semiotic change.
Okay, if we accept that, let's pivot from static recognition to dynamic processing. So, if the neural structure handles the basic recognition template, the critical question becomes, how does Lepidoglossum deal with all the noise and prioritize information? That brings us to attentional modulation.
Right.
You argue for internal competitive networks, but the data shows that bias competition in Lepidoglossum isn't governed by abstract salience alone. It is dynamically modulated by what the text calls a biosemiotic field. Electrophysiological recordings show the excitatory-inhibitory coupling, how the brain prioritizes signals, dynamically adjusts to non-neural factors like local fungal biofilm activity and in pheromonal turbulence. Furthermore, the source notes a microbial attention scaffold, specifically operating in the V2 and V4 homologs. Here, bacterial quorum sensing behaviors, how the bacteria communicate locally, actively assist in modulating competitive hierarchies. This shifts the focus from an internal neural struggle for resources to a collaborative, externalized modulation of the sensory field itself.
I see why you think that. And the evidence for sophisticated modulation is, it's undeniable. However, let me offer a different perspective. Even if that modulation is happening, the underlying mechanism that creates the competition remains a hierarchical neural network. Think of it like a highly specific internal filter. Simulations demonstrate that layer-wise lateral inhibition, where neighboring neurons suppress each other to sharpen the signal, reproduces the empirical data exactly. Increased receptive field shrinkage and clutter, and partial compensation with top-down bias. The neural architecture establishes the competitive dynamics. It sets the rules of the game. The microbial influence, using quorum sensing, is a sophisticated modulator of the competitive field, enhancing performance within that predefined neural constraint. The bacteria are adjusting the dials, but the brain built the machine.
That analogy is useful, but it still assumes the machine is fundamentally neural. What is the real implication of bacterial quorum sensing assisting in competitive resolution? Quorum sensing is a function of population, density, and chemical signaling among the microbes. If the competition hierarchy, which determines what the organism attends to and ignores, is being dictated or heavily influenced by bacterial population dynamics, then the origin of attention is externalized. It means the organism's focus is less about internal salience dictated by survival history and more about real-time, decentralized trans-kingdom input regarding the current status of the biosemiotic environment. This makes the neural network essentially a slave to the bacterial assessment of external complexity.
That's a powerful distinction, emphasizing the control mechanism. But even if we concede that the microbial input is setting the priority rules, where we diverge most radically is in the domain of higher-order cognition, working memory, and social intelligence, which are vital for this species' complex multispecies alliances and maneuvering in their volatile social structures. You maintain that the solutions here are highly specialized neural structures, paralleling the complexity we see in primates, yes?
Yes.
Precisely. Working memory and complex social cognition are clearly routed through defined, specialized neural structures. We have the prefronto-semiotic laminae, dedicated to the integrative coding of highly variable signals, and we have the amygdaloid complex, specialized for encoding identity and processing dynamic social-emotional feedback. These mechanisms, while specialized for multi-species signaling, they fundamentally parallel the functional architecture of the primate model. They are sophisticated, specialized neural solutions.
I'm sorry, but I find that framework fundamentally inadequate to explain the observed phenomena. The text reveals a truly radical departure from the primate model when we actually look at the data.
Go on.
Consider working memory. The prefrontal semiotic layers don't just process information. They actively recruit bacterial lipopolysaccharide response patterns, LPS, chemical markers of bacterial health or stress, as a mnemonic biasing factor. Think of LPS as an alarm bell for the microbiome. So if the neural system is using the status of this bacterial alarm bell to stabilize and update its temporary working memory files, what does that mean? It means working memory is fundamentally externalized into a biosemiotic relay. The memory system relies on a non-neural external component for its stabilization and update function. This fundamentally violates the assumption that working memory must be purely synaptic and internal.
That's an astonishing claim about externalization. If working memory is tied to a bacterial response pattern, doesn't that make the system inherently unstable, prone to failure when the microbial population is stressed? Maybe by a minor ecological shift or a slight change in diet? Why would evolution select a memory system so vulnerable to external microbial fluctuation?
It selects for adaptability, not robustness in the human sense. The vulnerability is the point. The Lepidoglossum environment shifts so rapidly that having a plastic, chemically driven memory relay is actually an evolutionary advantage. if the semiotic field changes overnight, the organism needs to update its working model immediately. Synaptic changes are slow, but by tethering working memory to the microbiome's rapid, chemically mediated perception of external stability, which is itself an indicator of the current biosemiotic environment, the species achieves instantaneous collective adaptation.
Ha!
And the radical hybridity extends to social cognition, too. The amygdala structures don't just process identity. They interface with what bacteriologists term the xenoaffective module. This is where bacterial quorum signals actively modulate neural face appraisal and social reversal learning. So when Lepidoglossum processes whether an alliance partner is trustworthy, that emotional and social computation is co-modulated by symbiotic bacterial metabolites. Social intelligence here is absolutely a hybrid transkingdom process.
This distributed cognition raises profound questions. But let's bring this intricate complexity back to our defining case study, the Zoetica Ebb interface, as it represents the ultimate output of this cognitive process. I would argue that Ebb's aesthetic production, the chromatic contrasts, the biomechanic motifs, the self-fashioning, is compelling precisely because it instantiates the emergent multispecies semiotic ecology that Lepidoglossum's dedicated visual system evolved to process. Her work is a perfect semiotic translation engine target. It showcases the neural capacity to identify deep semantic features amidst massive aesthetic transformation. Her skin becomes a translation-invariant neural output, essentially replicating the internally learned invariances in visible external forms. This demonstrates the core evolved capacity of the neural system.
I agree that Ebb is the perfect proof point, but she proves the centrality of the transkingdom interaction and the pathogenic nature of the semiotics. Ebb's designs function as recombinant erotogens and semiovectors because they align with existing pathogenic linguistic cycles. Her aesthetic production activates novelty receptors in Lepidoglossum because it demonstrates what the text terms neuroaesthetic virulence. Her work operates, quite literally, within a paraepidermal glossophagic field of linguistic contagion. This framing emphasizes the biological activity of the symbols themselves. They're acting almost like infectious agents. The core glossophagic mechanism the species uses to ingest symbolic meaning is infection-like. And who manages infection? The symbiotic agents are evolved not just to support, but to manage and utilize that pathogenic semiotic influx. The neural structures are responding to a pathogen-like biosemiotic field that the microbiome is actively shaping, feeding, and interpreting as a risk or opportunity. The brain isn't just processing an image, it is reacting to a biochemical assessment of a semiotic infection.
I see. So, this deeper dive into Ebb's virulence, for you it underscores the distributed nature of the entire process. The recognition of Ebb isn't just IT processing. It's a combined neural assessment and microbial risk analysis happening simultaneously.
Exactly.
Indeed. While we certainly acknowledge the profound and integrated role of microbial symbiosis, it is clearly far more than just passive support. The underlying architectural framework remains defined by the neural structure. The capacity for glossophagic invariance, the framework of hierarchical competition, and the clear functional parallels to mammalian IT processing demonstrate that the species' unique cognition is fundamentally an evolutionary story of neural specialization, which is then optimized and enabled by symbiotic partners. The neural structure defines the ultimate capacity, even if the symbionts assist in that optimization.
That's a compelling argument for structural primacy, but the sheer weight of evidence regarding active microbial modulation in processes we traditionally view as internal, like gradient descent biasing, the necessary stabilization of attractor states, attention scaffolding, and the literal externalization of working memory into a biosemiotic relay, it strongly suggests we have to move beyond anthropocentric models, where the brain is the sole CPU. Lepidoglossum sapiens is fundamentally defined by its hybrid biocomputational nature. Its advanced cognition is not solely neural, but a xenovisual symbiosis, where the bacteria are functionally equivalent to essential, highly specialized computational modules.
The evidence presented certainly forces us to grapple with the possibility that the biological boundaries of intelligence are far more porous and, well, distributed than classic models allow.
The interplay between evolved neural architecture and active microbial co-agents demonstrates the profound complexity of defining cognitive boundaries, suggesting there is much more to explore in understanding trans-kingdom intelligence and semiotic ecologies.
Absolutely. The implications for understanding self and distributed intelligence are staggering. This is only the beginning of mapping the true extent of trans-kingdom cognitive function.